This is Unit 10, Lesson 4, Surface Area and Volume of Composite Solids. A composite solid is simply when you take two solids, and we've been doing solids all through Unit 10, anytime you take two of those solids and you put them together in some form. This first figure is where I'm just going to take two solids, in this case a cylinder and a rectangular prism, and I'm just going to put them together and I'm going to say they're one thing, and I'm going to find the surface area or the volume of that entire figure. Now, sometimes we put them together like this. This is actually a rectangular prism with a cylinder like drilled out of the center. It's been removed. So this is actually a void in the middle, and we would use the fact that we know the size and the shape of that cylinder in the middle to determine what was left of the rectangular prism. So when we're doing surface area of solid figures, composite solids, we want to determine what solids we have. Do we have rectangles? Do we have triangles? Do we have pyramids? Do we have cones? Do we have spheres? All of those, we want to determine what we have. Then we want to determine how they're being combined together. Are we adding them together? We're just sticking them together and saying they're one thing. Or are we removing one shape from the other one? And then when we're working with area, we have to take into account that when we put two figures together, there's going to be some overlapping space. So if we were finding the surface area of this figure, we would not want to take into account, we'd want to subtract or remove that space where the circle sits, actually touches the rectangular prism. And in the case of removing it, we want to take into account not only is the body of the cylinder removed from the center of the prism, this on each end, on the base at the top and the base on the bottom, the base of that circle, that's also missing from that figure. So we have to take all of those things into account with surface area and volume. This first problem is finding the surface area of a hemisphere. So first thing you need to realize is that a hemisphere is just half of a sphere. So we're going to start with the formula for a sphere. The surface area of a sphere is pi, or 4 pi r squared. We want to find half of a sphere, so I'm just going to take this 4 and I'm going to cut it in half. I'm going to say that for half of a sphere, we're going to say 2, you can say 4 over 2 or just 2 pi r squared. Then we want to determine our variables. Well, the nice thing about a sphere is that we only have an r, we have a radius, and the radius is not 8, this is a diameter, so we're going to cut that in half. So our radius is 4 yards, and we're going to substitute that in. The sphere is 4 halves pi 4 squared. And I'm just going to put that in my calculator. I'm not going to try and make my life more difficult than it is. All right, alpha y equals 4 over 2. And then we're going to go pi button and 4 squared. So the surface area of that hemisphere, rounded to the nearest hundredth, is 100.53. So 100.53. Now, don't forget, because this is a hemisphere, it now has a flat bottom. And this formula does not take into account that flat bottom. This formula only takes into account that dome shape. So this 100 yards or so only is the dome that covers it. We also need to find the area of that flat bottom. So what we'll need to do is do the area of a circle, which is pi r squared. So we'll go second pi 4 squared, and we'll find that it's 50.27. That's also in yards squared, and this is yards squared. And we're just going to add those two things together to get the total surface area of that hemisphere. Comes out to 150.8 yards squared. Now, in our second example, we're going to look at two cylinders. One cylinder has been removed from the inside of the first one. So we're going to find the surface area of the large cylinder. We're going to find the surface area of the small cylinder, and then we're going to subtract those things from one another. So we're going to find the surface area of the large cylinder. So the formula for cylinder is 2 pi r times the height of the cylinder plus 2 pi r squared. So we're going to plug in our numbers. The nice thing about this is we're looking at the large one. So the radius of the large cylinder is 7, and the height of the large cylinder is 6. So 2 pi 7 times 6 plus 2 pi 7 squared. And I'm going to put all of that in my calculator. So 2 pi 7 times 6 plus 2 pi 7 squared. So the surface area of the large cylinder is 571.77, and it's measured in millimeters. And in the notes, this is broken down as finding the lateral surface area and then finding the area of the bases. And there's a reason for this. I don't want you to find the total surface area of that cylinder, because when we take the cylinder out, we're going to have a hole in the middle of the big cylinder. Well, we need to know the surface area of the interior of the big cylinder where that hole is missing. But then we also need to remove the space where this cylinder had a base, because now that's just an empty place. So we're going to calculate two different things because we need to take into account the bases of the small cylinder are just drilled away. They're gone. But we've exposed surface area inside the large cylinder, and we need to figure out that. So that's what we do when we find the lateral surface area. So the lateral surface area of a cylinder is 2 pi r h. When we find that lateral surface area, that will be what's exposed inside the big cylinder. So 2 pi. Now the radius of the small cylinder is different. The radius of the small cylinder is 3. But the height's the same. It's nothing changed there. So the lateral surface area is 2 pi times 3 times 6, which is 113.1. Notice, I want you to see this on the calculator. We're going to round to the nearest hundredth. Well, the 7 tells you to round the 9 up. Well, 9 rounds to 10, so that's actually going to turn that 0 into a 1. It's kind of like a domino effect when we start rounding some of those numbers. Then we want to find the area of the bases. So we're going to go ahead and we're going to use this formula because there are two bases to that cylinder. So the area of the bases is 2 pi r squared. R is still 3. This will cube that for some reason. This will, instead of finding the area of just one base and subtracting it, there are two bases, so we need to subtract both of them. So we'll say 2, because there's two bases, times pi times the radius squared. And we find that both of the bases together have an area of 56.55 millimeters. So we're going to start with this 571 because that's the entire big cylinder. And then we're going to add, actually let's do it in the order that it's written in the notes. We're going to subtract the two bases. We're going to subtract because these two things, this flat space and this flat space, disappear. So we're going to subtract the 56.55. And then we're going to add in the 113.1 because now that this round space has been exposed, and we want to show that in our formula. And we're just going to add all these numbers together and subtract. So I'm just going to do it all at once. 571 minus 56 plus 113, and I am typing all the decimals in. It's not saying them. So the total surface area of this composite figure is 628.32 millimeters squared. Surface area problems, they're kind of a hassle. Volume problems are a little bit easier though. So let's look at some composite volume figures. All right, so the first composite, and it's the same idea. Sometimes you're going to have things that are being put together. Sometimes you're going to have things that are being taken out of a figure. So in example 4, we've got a cone and a cylinder that have been put together. And in example 3, we have a prism, a rectangular prism, and these dotted lines, it's not the greatest way to explain it, but if you read the directions, find the volume of a prism after the pyramid has been removed. So this pyramid shape that's in here has been taken out of that figure. So we're going to figure out what we've got first. We've got a rectangular prism. And we have got by default, a rectangular or square pyramid. So the volume formula is pretty simple. Volume equals the area of the base times the height of the figure for a prism. So because it's a rectangular prism, it's going to be the volume is the length times the width times the height. And for my rectangular pyramid, the difference in a pyramid and a prism is that 1/3. A pyramid is 1/3 the size of a prism with the same base. So this is going to be 1/3 the area of the base times the height, or 1/3 the length times the width times the height. So we want to make sure we know what all our variables are. The length of so let's use the bottom of this as our base. We'll say that this is our base. So the length is 25 and the width is 12. And then the distance between the two rectangles is 15 feet. So that's the height. Remember, the height is not how tall it is. The height is the distance between the two parallel bases. And then we're just going to substitute these numbers in here. Volume equals 25 times 12 times 15. And so the volume of the prism is 4,500 feet cubed. Remember, we're dealing with volume now, so it's cubic. And we'll do volume is 1/3 of 25 times 12 times 15. So the volume of the pyramid that's being drilled out is 1,500 feet cubed. Now, because that pyramid's being taken out, we need to subtract. So we're going to take the original prism minus the pyramid that's being drilled out of its center, and we're going to find that the prism is left with 3,000 cubic feet of space in it. I like the volume problems. They're sometimes a lot easier because you don't have to take into account all the overlapping and disappearing and reappearing sides of the figure. So, example number 4. Example number 4 asks you to find the volume of a cylindrical package with a cone-shaped top. That's nice. They tell you what the shapes are. We have a cylinder, and we have a cone. So, the formula for the volume of a cylinder is still that capital B. That's the area of the base times the height. If we make it more specific to a cone, the area formula for a cone, for the base of a cone, or the area formula for a circle is pi r squared, and then how far are those two circles apart from one another. And then for a cylinder, I just did that backwards, so let's do this. Talking about the cone and writing the stuff for the cylinder, let's just relabel this. That's the cone, this is the cylinder. We need the area of the base, so we need the area of the circle on the bottom, and then we need to know how far apart the two circles are. And then for a cone, because a cone is related to a cylinder, we're going to do 1/3, because a cone is 1/3 the size of a cylinder with the same base. That capital B times H, so it's going to be 1/3 pi r squared times the height. Now, the nice thing about circles is there's always fewer numbers to deal with. So the radius, this is a 16. This 16 is not the radius. This 16 is the diameter because it goes all the way across. I only want to go halfway. So I say 16 divided in half is 8. So that's the radius of both the cone and the cylinder. Now, we need to find the height of the cone. So we need to know how far it is from the apex of the cone to the bottom, and we need to find the height of the cylinder. So they've given us the height of the cylinder. They said, hey, the cylinder is 19. So this is the cylinder. I'm going to label these so we don't get them mixed up. And then they tell us that the height of the entire figure is 32. Well, if I know the entire thing is 32 millimeters, and I've used 19 of those millimeters for the cone, then I can find the height, or I've used 19 of those for the cylinder. I can find the height of the cone by saying 32 minus 19, and 32 minus 19 is 13. So that gives me the height of the cone. And then all I have to do is substitute those things in. So for the cone formula, volume equals 1/3 pi, the radius is 8 squared, and the height of the cone, here's the height of the cone, is 13. When we multiply all of that together and round, we find that the cone has a volume of 871.27 millimeters cubed. And then we're going to do the cylinder. And the cylinder volume equals pi times the radius squared times the height of the cone, which is 19. So we find that the volume of the cone is 3,820.18 millimeters cubed. Now, we found these two separate numbers. It's one figure, so we want to add those things together. 871.27 plus 3,820.18 all adds up to equal 4,691.45 millimeters cubed. When you're doing composite figures, make sure you know whether you're looking for volume or surface area. Make sure that you know what figures you're dealing with. Are you dealing with prisms? Are you dealing with pyramids? Are you dealing with spheres? And make sure that when you're doing surface area, you take into account where those things overlap. Make sure you understand that things are being put together, so you're going to have to add things together. Make sure that if you see that things are being removed from one another, then you will need to do some subtraction.